Assalamu alaikum. Hi everyone. Welcome to our webinar AI top-down reservoir modeling. I'm Abdullah Abdurrahman, a business developer into reservoir solutions. I will do 5 minutes presentation, then Mr. or Professor Muhajiz will start the webinar. Reservoir Solutions is a company specialized in providing technical studies and courses for oil and gas companies and professionals. The company incorporates many professionals with diverse technical background related to oil and gas exploration and production. Our services include technical reservoir studies, field development planning, reservoir static and dynamic modeling, economic feasibility studies, technical support for academic researches like PhD and master degrees. Also, we are assisting in writing technical papers and publishment. We are also providing technical petroleum courses by industry expertise, and we are providing mentorship programs. Before introducing Mr. or Professor Shahab, I wanted to introduce 2 upcoming courses for our company. The first course will be about hydraulic fracturing, pre-job design, execution, and post-job evaluation. That course will start tomorrow, inshallah. By the end of this course, you will be able to know the application for hydraulic fracturing. You can also select the candidate for hydraulic fracturing. You will know the operation sequence for hydraulic fracturing. Also, you will estimate the geomechanical properties for your reservoir that will be candidate for the hydraulic fracturing. You can select the propellant fluids and additives for the job. Also, you will do diagnosis for an analysis for the tests that will be required for design the hydraulic fracturing job, like the mini frac analysis. Also, after the job, you will be able to do QC for the job. All the analysis will be done and you will know how to do this analysis. The package for this course will include lifetime access to recorded sessions, application datasets, application-based workshop. Also, we are providing the course material. You will have open discussion with instructor during and also after the course. At the end of the course, you will have a certificate with online identification ID on our website. The second course, it will start on 10th of September. That course, it's called Borehole Image Log Processing and Interpretation. It will be 2 weeks hands-on experience workshop for the processing and interpretation. By the end of this course, you will know the borehole image application. You can do processing for the image log data. You can also do manual deep picking, interpret reservoir structure and stratigraphic, do structure depth analysis, know how to make this azimuth vector outplot, calibrate image by core data, interpret wireline logs with borehole images, learn porosity evaluation and texture identification for carbonates, do fracture characterization and interpretation, thin bed evaluation by texture identification and sand counting, and do processing and interpretation for acoustic log. Okay. The course content for the 2 courses will be sent onto the Zoom chat. So if you wanted to have more details about these upcoming courses, you can review into the Zoom chat. About our today webinar instructor, it will be Professor Shahab Muhajiz. Professor Shahab Muhajiz, a pioneer in application of artificial intelligence and machine learning into the exploration and production industry. He is a professor of petroleum and natural gas engineering at West Virginia University and the president and CEO of Intelligent Solutions Company. He is director of West Virginia Laboratory for Engineering Application of Data Science, including more than 30 years of research and development in petroleum engineering application of artificial intelligence and machine learning. He had authored 4 books, shale analytics, data-driven reservoir modeling, application of data-driven analytics for the geological storage of CO2, and smart proxy modeling. More than 230 technical papers and carried out more than 60 projects for independent national oil companies and international oil companies. He is a SPE distinguished lecturer from 2007 to 22, and he has featured 4 times as distinguished author in SPE's Journal of Petroleum Technology, GPT. He is founder of SPE technical section dedicated to artificial intelligence and machine learning. He has been honored by the U.S. Secretary of Energy for his artificial intelligence-based technical contribution into aftermath of Deepwater Horizon. He was a member of the U.S. Secretary of Energy's Technical Advisory Committee of Unconventional Resources in 2 administrations. He represented the United States into the International Standard Organization on Carbon Capture and Storage Technical Committee from 2014 to 2016. As usual, the webinar rules will be: first, if you have any question, you can drop your question into the Zoom chat so that instructor will answer after the webinar. Mute your microphone and camera. In case that you wanted to have a certificate for attendance, you can fill into the form that will be sent into the Zoom chat. For upcoming courses and webinars, you can join our Telegram group that will be updated day by day, and that our mail and also our WhatsApp. Thank you all, and hope you a nice learning journey. And Professor Shahab, you can start now.
Good afternoon, everyone. Thank you for paying attention to this topic. Let me share my screen. Please let me know if you can see the screen. So,
yes, you can. Yeah, I can see.
Very good. All right. So the topic of this particular presentation is AI-based top-down reservoir simulation and modeling. And what is the requirement of AI-based reservoir modeling? What do you need to know in order to be able to do this? First and foremost, you have to be an expert in reservoir engineering. And also, you have to also be an expert in artificial intelligence. If you do not have both of these characteristics, then it's going to be really tough for you to do this. So when it comes to reservoir engineering, as an expert, you know that fluid flow in porous media is a function of both space and time. And for numerical reservoir simulation or for any type of reservoir modeling, what we do is a full field reservoir model, not a single well modeling. Another very important issue, and that's what separates what we have done in the past time with a lot of companies or service companies that actually will tell you they're doing AI for reservoir. That's the main difference between us and them. We do full field reservoir model, but we do not do decline curve analysis. And that's the major difference. As a reservoir engineers, hopefully you know the big difference between these two. And again, as a very important issue, we have to we have to realize the importance of geology in reservoir modeling, knowing issues such as well logs, cores, seismic, and so forth. And when it comes to expertise of artificial intelligence, again, let's see what we need to know. We need to know the history of this technology. We need to know the correct definitions of this technology. If you have been exposed to some of these companies, service companies in our industry, and they define AI, you clearly, I'm going to give you the definition, and you can clearly see how different their definition is of what artificial intelligence and machine learning is. The definition of this technology should be identified by those people, by those scientists that actually developed this technology, rather than we create our own definition of what this is in order for it to work. But anyways, then another very important part is the application of AI, artificial intelligence, in science and engineering, which is quite different from general intelligence. Then it's very important to know how to model physics using AI. Which is quite different the way we have been modeling physics in the past century as engineers. Another very, very, very important issue that I'm going to cover here and explain it to engineers is ethics of artificial intelligence. And it's very important to engineering as well, and specifically to reservoir modeling. And overwhelming majority of people and companies, service companies, and the vendors that today they say they do AI for petroleum engineering, just ask them what is ethics of artificial intelligence, and they probably have no idea what that technology or what this issue is that have been around for a decade right now. It's very, very important, and there is actually there is application of this ethics in petroleum engineering, very, very specific and very important in engineering and science in general, in our industry, very specific. And of course, then it comes the issue of explainable artificial intelligence, which is again in our industry is very important. So in that context, let me continue in this technology. So the outline of this presentation is I'm going to talk. It's right now 12 minutes after 6 for you, 12 minutes after 12 for me, and that being said, no more than 45 minutes. So it is impossible for me to cover all of these in details. I do teach short courses for this technology, and we can go into a lot of detail sometimes, or there are books that have been published as well. And if you're interested, I give you the details on that. But today, very quickly, I'll talk about the definition and modeling physics and ethics. These are the most important things first. And then I'm going to talk about the reservoir modeling using this technology, the difference between AI-based reservoir modeling and numerical reservoir simulation, which we have been doing for about 70 years. And actually, as you know, I'm a reservoir engineer, and I'm a professor at West Virginia University, and I've been teaching numerical reservoir simulation for about 25 years. And it's a great technology, don't get me wrong, but the fact is it's different between that and using AI. And then I'm going to talk about intelligent data patching, geoanalytics, which is AI-based geological modeling, and fully automated history matching and blind validation of AI-based reservoir simulation. And I'm going to talk about dynamic production allocation. These are the things we do in reservoir simulation. It's very, very important, but I'm going to show you how we do it in AI and what the results is. And finally, the most important one, after you do all of that, the key is how do you use it in OPEX and CAPEX optimization? And I show you actual case studies that we have done on this topic. OPEX, of course, is operation is when the company spends the money on the wells that exist to increase production, and CAPEX is when they spend the money to drill new wells in order to do that. So let's talk about the correct definition of AI. If you look at SPE, they had put together a article from some people a few months ago, and one of the things they did, they provided definition of AI and machine learning. That definition was incorrect, unfortunately. The reason was their definition. I think the correct thing is the definition of AI and machine learning. We should refer to the definition of the people who created this technology, not the ones that trying to use it, and they're not able to use it correctly. So with that, first let me tell you about what happened historically, and then the definition of AI makes sense. First and foremost, we are all Homo sapiens, and we as Homo sapiens came to what today is called Middle East and Europe about 70,000 years ago. And that's when the cognitive revolution took place. And I can go into a lot of detail in all of these techniques if you have any questions. But anyways, after we did that, it took us about 58,000 years until we made a big difference. And we had our first revolution after cognitive revolution, that was architectural revolution. And that changed everything, where we no longer were hunter-gatherers in the past 58 years, and then became agricultural people. And then it took another 10,000 years, or actually more than that, until we had another big revolution. And that revolution that happened in mid-18th century was what we call the Industrial Revolution. And that's how it became people like you, engineers. And now this is the big thing, that the current biotech, that if you're interested, I can explain that to you as well. And artificial intelligence is a new revolution that actually happened in mid-80s, and it's going to change everything in our life within the next couple of decades. As engineers, you will have to know this technology, and you will be using this technology in the future. So in that context, what is artificial intelligence? Artificial intelligence is the technology that simulates human intelligence. This is the key words, folks. It simulates human intelligence. That's why it's called artificial intelligence. How does it do that? It does it through mimicking human brain. So it's all about human brain. It mimics human brain in order to perform analysis, to do modeling, and to do decision-making. This is the realistic definition of AI, and that is not my definition. This is the definition of the people who created this technology. How about machine learning? Machine learning is the science of making computers to act without being explicitly programmed. So as you know, for example, as reservoir engineers, one of the things we do, we build numerical reservoir simulation. Then what does computer do for us? Computer does exactly what we tell it. Explicitly, we explicitly program, and we tell the computer what to do, cell by cell, in so much detail. In other words, computer doesn't do anything that we don't tell it to do. That is the regular one. What is machine learning? Machine learning doesn't do that. Machine learning is open computer algorithm. That algorithm is not exactly do what we tell it to do. It learns from the data we provide to it. So the same algorithm, which is an open computer algorithm, can be applied in so many different problems. It all has to do with the data that you provide for different problems, and it can solve it. So it's an open computer algorithm, and it's not an explicitly programmed algorithm. That's the definition. So first and foremost, what I need to show you is what machine learning algorithms that we have to use. In here it says smart proxy modeling, but the same thing, that's something I'll discuss it later. But the same is true for the reservoir simulation modeling that I'm explaining to you. We use these three machine learning algorithms: artificial neural network, fuzzy set theory, and genetic algorithm. And what they do in artificial neural network, human brain information is processed. In fuzzy set theory, human logic is processed. And in genetic algorithm, optimization is done through natural selection. I'm not going to go to the detail of this, but this is just to let you know what the difference is, because we're going to concentrate on reservoir engineering. So modeling physics using artificial intelligence is also very important. So physical phenomena is modeled and solved using mathematical equation as engineers that we are. I give you an example, rocket trajectory. So these things that right now because when countries fight with each other and have the war, that's what they do. They hit the rocket and it hits it somewhere. How do they know where to hit it? Well, as you know, that's a mathematical equation that identifies where it has to go, and it has a function of initial velocity and this angle to identify the range. Where does it go? So, right, it's an equation that tells us how to do that, right? So, throwing something, but how does human brain deal with that? This is almost the same thing in football, in American football. They throw the ball and the other one goes and catch it, right? So does human brain go ahead and create this mathematical equation and solve it, and then tells the muscles and your feet to run in which direction and your hands where to get it? Is that what human brain does? I think it's very obvious. No, human brain does not build a mathematical equation in order to solve this physical phenomenon. So then how does human brain solve physical-based problem? Imagine doing this. This is a very, very complex things to do, using your hand in order to keep that thing in your hand. So how does human brain does that? It does it through observation. It does it through learning. It does it through training, trail and error, back and forth. It does it through all the things that it sees, actual data used by human brain, right? But there is uncertainty with the actual data. There are noise with the actual data. Nevertheless, our human brain can still handle that. Since AI mimics human brain, can it do the same thing? Use actual data to solve physics-based problem? Absolutely, yes. That's what we're doing in this numerical reservoir simulation not numerical, but AI-based reservoir simulation that we will be covering for you. So once proven that physics can be modeled with AI using data, what does that mean? Well, that means that AI-based model of physical phenomena, like reservoir modeling, can be developed using real measured data, actual measured data, not calculated data. This would serve as an alternative to traditional modeling of physical phenomena. Again, we've been solving reservoir models for almost a century. This is a new version of doing that. It's not the same thing. Very quickly, a lot of people say that they know AI very well because they read a book or whatever. I want to ask you something. Does this make sense to you? If some company come and say, we can create a master physicist in just 1 month. Does that make sense? If a company says that we're going to create a master chemical engineer in just 1 month, master mechanical engineer in 1 month, or a master petroleum engineer in just 1 month, does it make sense to you? None of these that I showed you is true. No company ever has said that. I just made this up. Why? Why did I make this up? This is not real. No company has ever done that. Let me show you why I made this up. You see this? Master data science, just 1 month. This is real. This is actual. This is a company that does that. And a lot of people that call themselves data scientists is because they go and get this 1 month. So my point is, that's a problem currently we have in our industry. A lot of people call themselves data scientists, and a lot of some service companies come to the other companies, come to the producers and tell them, we can do AI for you. And if you ask them, how long did you have learned? that tells you so. With that said, I'm going to say one more thing, then I'm going to go to reservoir engineering. And that's incredibly important. No engineer has ever paid any attention to this, unfortunately. It's called ethics of artificial intelligence, AI ethics. What is it? Well, folks, ethics of artificial intelligence became a research topic. How? Because racism and sexism was created by AI-based model in the past decade. If you don't know that, do some research, you'll find out. Just do it, go to Google and you find out a lot of information on this. Companies such as IBM, Google, Amazon, a lot of these build AI-based model that they were generated racism and sexism. Of course, they did it unintentionally 10 years ago when they did that. They didn't mean to do that. But the reality was they created a lot of racism and sexism. I'm not going to go into the detail. I actually teach a course on that. And this racism, using AI model, they created that and have made efforts. Then when they found out that what they created called racism and sexism, then they did research to address why. How did we bias? We created the bias inside the AI model. One solution for addressing the bias is to create a documentation for the data that was used to build the AI system. Keep that in mind. Thesis has nothing to do with engineering at the beginning, right? This was created, actually, let me show you, in MIT, one of the best universities in the world, and specifically in the United States. They created a whole AI-based place based on what happened. This is what they say in one of their articles. Again, please go ahead and do research, and this is very important. The problem of bias, racism and sexism and everything, all these bias, in machine learning is likely to become more significant as the technology spreads to critical areas like medicine, like law. I added this, they didn't say it, like engineering, and I tell you why. And as more people without a deep technical understanding are tasked with deploying it. So keep that in mind. And then they continue saying, in MIT said, some experts, remember I said expertise is incredibly important in engineering, warn that algorithmic bias is already pervasive in many industries. That's what I'm talking about. That's why I said, and because it's literally an issue in our, and I show you in a minute, that almost no one is making an effort to identify and to correct it. This happens so much in our industry. Let me explain it to you. They also says that Google's AI chief says that to forget what Elon Musk said about killer robots and worry about AI ethics, the biases that exist. This is again from MIT. So what is AI ethics in petroleum engineering? That's called hybrid models. So that's why a lot of companies tell you they do hybrid models. So let me show you why hybrid model is engineering AI ethics. AI-based models of physics is purely based on fact, based on reality, based on actual measurement. Traditional physics-based models that we've been doing in the past 70 years or the past century includes some of the following items through mathematical equation. It includes assumption, it includes interpretation, it includes simplification, and even we can include their preconceived notion and biases if we want. By including data from mathematical equation to actual measurement, you are telling AI-based what to do. That is known as bias. When they say hybrid model, they bring actual data that they generated from mathematical equation that they already tell what AI to do, and they add it to the actual one, and I show it to you. So let me give you an example. This is an offshore field in Southeast Asia. On the y-axis, you have oil production, and in x-axis here, you have gas lift, you have completion, you have porosity, and you can see the data. This is actual data. It's a conventional field. This is the same thing from a Marcellus Shale in Pennsylvania, US. It's unconventional, but you see the data. It's all over the place. There is no pattern to it. So when you get this data, let's assume that this is the actual field measurement that you have. The objective is to use this data to develop an AI-based model, right? We've been doing that for a long, long time. Now, some companies started doing that, and they were unsuccessful. They were not able to generate an AI-based model from this. So what do? Then, if AI approach does not work, what would you do? What would these people have done already? Well, they build hybrid model. How? They use mathematical equation to generate data and then combine that data with the actual measurement. So mathematical equation creates data that is already have pattern, has correlation. Why? Because that's the definition of mathematical equation. So they create data with mathematical equation and they add it to the actual data, and then they create a model. They actually can do the same thing in a different fashion, the same data, but they use a different mathematical equation, another company. It gives you another results. So it really doesn't, in these cases, what really means, it doesn't matter what the actual data is. It's all about the type of mathematical equation you use to generate the data. It's all about you, not about reality, not about AI. That's what hybrid model is. That's why you should stay away from it. So with that, now I'm going to talk about the AI-based top-down modeling versus numerical, which is a bottom-up reservoir modeling. First and foremost, traditional numerical reservoir simulation and modeling, which we have done for almost a century. Again, I've been teaching it. It's a great technology, don't get me wrong, but it's different from AI-based model. How? The traditional numerical reservoir simulation includes assumption, it includes simplification, that's the definition of numerical simulation, and it includes interpretation, right? However, it also can provide opportunity to include preconceived notion and biases. It all depends how you do this. How about AI-based model? It's purely based on fact. It's purely based on reality. It's purely based on actual measurement, nothing about what you can generate. So actual field measurements determine the quality of the reservoir model, not what you like to do, number one. The other one, it starts from geological model, the traditional numerical simulation that we have been doing for a long time. First, we go to GNG people, experts. We ask them to do a geological model. They give it to us, and then we try to history match the production. The production is on the top, geology, the reservoir is on the bottom. How about AI-based? We do it exactly the opposite. We start with the production from the top, and we use that in order to find the actual, the most important geological model that is in the reservoir. Let me give you a bit more explanation. So comparing these two, top-down versus numerical modeling, AI-based reservoir modeling takes an opposite approach when comparing it with numerical reservoir simulation. Imagine this is a field, right? The reservoir right here is in the bottom, and what do? We drill wells on the surface, don't we? And these drills go down to where the reservoir is, and then we do completion at the reservoir layer, right? To produce oil, gas on the top. Don't we do that? Yes. So this is what we call top. This is where you and I are. None of us go down 10,000 feet to find out what the reservoir is. We are on the surface, and this is what we see. However, what's down there, the completion of the drilling, that's what's in the bottom. Keep one thing in mind. that in numerical reservoir simulation, what do? We start from the bottom. We model the geological formation. I mean, geologists do that. They give it to us, and then we use that to history match what goes on the top. So it's bottom-up approach. So bottom-up modeling starts with the space and then brings in the time. And it does that through mathematical equation. That's the difference between AI-based. AI-based uses first the measured historical production that's on the top, all the oil, gas, water production that's on the top. And then it goes down and it says, okay, what kind of geology, reservoir created this production that we have? So top-down modeling starts with the time, not start with space. It starts with the time, and then it brings in space through field measurement. So that's the difference between numerical reservoir simulation and top-down modeling. One last thing, keep one thing in mind. When we do numerical reservoir simulation, we need flowing bottom hole pressure at the bottom. In top-down model, we don't need that. Why? Because we hardly ever have that as a measurement in historical data. What we do have and what we do use is what's on the top, not flowing bottom hole pressure, rather than wellhead pressure, choke setting, flow line pressure, things that goes on the top. And in that case, TDM is an AI-based, comprehensive, empirical, full-field reservoir simulation model that developed solely, based on field measurement. Well trajectory, logs, cores, well test, seismic, operational conditions, everything that we measure, and the history of production injection. TDM is an incredibly quick and fast and accurate reservoir model that is validating using blind history matching. I'm going to show you examples of that. TDM is autonomously updated. So when you build a TDM, literally every week and month and every 2 months, every year, anytime you want, you can update it, and you can do it so quickly, and you can actually have it work in real time rather than you send it. Anyways, as I mentioned, top-down modeling combines, it's a coupled model. It's combined the reservoir and the wellbore model and the operational conditions, such as choke setting, wellhead pressure and temperature, wellhead flow line pressure and temperature. These are input to the top-down model. Oil production is the main output of the production. If you do numerical reservoir simulation during history matching, it's the other way around. The oil becomes input and flowing bottom hole pressure is calculated. So anyway, in top-down model, these dynamic variables simultaneously history match oil, gas, water, reservoir pressure, and water saturation. So literally, how do we do that? We start with all the field measurement, all the static data that measured, all the dynamic data that has been measured, and this then we go through a very, very long time as expert systems, expert engineers, expert reservoir engineers, to make sure that we have quality control and quality assurance of the data that we have. To do well biography, completion biography, in the identification of offset wells for every well that is producing. Offset wells could be injection and production offset wells, both. Any missing data with reservoir layers, commingled production that takes place, and all of that details. Once we do that, then we try to do intelligent data patching, because we always in the history we have data that's missing. That's why, again, you do not use mathematical equation to regenerate that data. I'm going to show you what we do. And then you do dynamic conductivity mapping. I explained that as well. And then we do, using all of that, we do geoanalytic. This geoanalytic, we build geological modeling actually using. So based on all of that, we generate what we call spatial temporal data set, because everything is about space and time. Then we take that spatial temporal database and we automatically do a history match. To do history matching, when you do all of that, you just click a button. You do not just do that on a month or years. And this is the process of history matching that takes place. The model input is all the spatial temporal database that you worked on that here, and you generating production, gas, oil and gas and water and pressure and saturation for the entire reservoir, not for only a single well. And what you do blind validation. I explained that what that means. I'm not going to use all of the data to build a history match. I'm going to use some of it and put it away to see if I can predict it well. If that doesn't work well, what does that mean? That means I have to go back and identify what mistake I made or what I should have done that I didn't in the data. But once you get it done, then you can do production forecasting, you can do sensitivity analysis, you can do uncertainty quantification, you can do infill location optimization, production optimization, injection optimization, completion optimization, reservoir layer production optimization, and so forth. So intelligent data patching, how do we do that? Handling missing data. So literally what I'm going to show you is how do we do that we use AI and a machine learning algorithm to do this, not mathematical equation. One of the major characteristics of a mature field is the fact that always some statistic and some dynamic data is missing historically. So you have three types of wells. You have wells that have all the data you need. You have wells with partially missing data, and you have wells with no missing data. So actually, as the size of these, you can see overwhelming majority of the wells are wells with partially missing data. Some of them, a very small one of them has no missing data, but there are still some that has completely missing data. So you have to deal with that. So if they have no missing data, what does that mean? That means in the top you have liquid, is oil and gas production as a function of time, date, and then you have wellhead pressure on the bottom. If you see that for every production, you have wellhead pressure. And let's assume wellhead pressure is missing, right? So there is no missing data. Everywhere we have production, we have wellhead pressure, right? When it's partially missing, as you can see here you have production, but you don't have wellhead pressure. Here you have production, but you don't have wellhead pressure. Here, and you see, so there are times that you have production, but not wellhead pressure. That's a lot of wells have that partially missing data. And of course, if it's completely missing data, you do have the production, but you have no wellhead pressure. That's completely missing data. The question is, how do you handle this? So what you're looking at, if this is the entire date that this one well, let's say, from beginning to the end, what you see this particular well in this date from beginning to the end of it has three colors. When you see the green color, that means you have the production and you have the wellhead. When you see the red, that means you have you have the production, but there is missing wellhead pressure. And when you see black, that means there is no oil production. That was, you don't need any wellhead pressure, right? So when you see, if you look at this is an actual well, you have about 20% of the wellhead pressure is missing. You do that for every single well in the system that you have, and you can see some of them have 100% missing, some of them have 16%, some of them have 80%. So this is what you can see, the data that's available, data that's missing, the data that there is no production. So how do you handle that? So we call it blind validation of intelligent data patching. So entire well, here's an entire well that we have the production. This is the well right here. This is actually a field in the Southeast Asia that we're working with. So for this particular well, we have the production and we do have the wellhead pressure. And let's say wellhead pressure is missing. This is true for every variable. So we say, okay, we do have all the data. So I'm going to leave this. I'm not going to use this to build the model, but I'm going to leave this. I'm going to call it a blind validation, because the model that I built that gives me the missing data, then I can compare it with the actual data that I have to see if my AI-based missing data characterization is correct. Look at the system that we did. The line that you see here in blue, that's the one we did with AI. We generated wellhead pressure from all the other data that exist in order to find out what would be the data that's missing. So in other words, what I'm trying to say, we do not use a mathematical equation to generate this data for this missing data, but because when you do that and you see that your AI-based data generation works well with the missing data, then you can trust what you have done and go ahead and generate the missing data. This is another well that we, for another field in another part of the platform in the same field. This was another data that we had, but we didn't use to build the model. But look, AI-based system that we made matched completely the same thing. So we can trust this and generate the data. Then what we do geoanalytics. When we do geoanalytics, so I have 10 minutes only. I'm going to do this very quick, then I'm going to show you the results without, I can't go into too much detail. So what is geoanalytics? In traditional numerical simulation, initial geological model is developed first to start the numerical reservoir simulation. And then initial geological model is developed based on spatial interpolation. However, in AI-based, geological model is developed using production history, and it is based on spatio-temporal space and time interpolation, not just the space. Now, let me explain it to you. So, in traditional numerical reservoir simulation, what do? First, we ask GNG people to build a geological model. They do it and they give it to us. We call it original basic geological model. It never results in a history match. What do we do as reservoir engineers? We start modifying that in order to get a history match. So how do we do that? We get the original geological model. We try to history match it, and it doesn't. We don't get good history match. So what do? We change the transmissibility modification in order to get for every single layer. We don't do that for the entire field. We do it for entire field, but on a well by well by well by well based. Because if you change everything, we never get history matched. So we modify this original reservoir geological model in order to get a history match. And this happens over and over and over and over again, because it takes us so long to do this. If you have done it in a real world, you know what I'm talking about. And then eventually we get a history match. And then if you look at the geological model that as reservoir engineers we did with compared to what we got from geological model, you can see how different the geological model became, right? And then we can use it production optimization. So traditional geological model uses well logs and cores and seismic. It does assumption, it does interpretation, and then it goes and it we use kriging or radial basis function, the geologists, and they do spatial interpolation. What does that mean? That means if you have these three wells, you have three porosity, then you do spatial interpolation between them. So between these two, between 10 and 4, it becomes in the middle 7. Between 10 and 16, in the middle becomes 13. Between 4 and 16, in the middle becomes 10, right? This is what's called spatial interpolation, not time, all right? However, this is what I'm going to show you. I want to show you what happens. If I do only a spatial interpolation, if I have these many wells, this is actually, it's an actual field in Southeast Asia we're doing this for. Existing production wells are these, and these are existing injection wells. And as they do a spatial interpolation, they create these values, and this becomes the gamma ray for the entire field when they have these values and they do spatial interpolation. This comes from, now let's show you what we do in AI-based. In AI-based, what do? We say, okay, while traditional numerical reservoir simulation is developed based on traditional geological model. So this is the geological modeling from reservoir formation. Then from that, we go to history match and do reservoir model. In AI-based, we do exactly the opposite. We do the reservoir model and we get a geological model. That's why it helps us to know where to drill the next well in order to get the results, correct, better results, to keep in mind that it's incredibly important that we let the fact tell us what's happening rather than we interpret and tell them what is going on. So let me give you an example of how it goes. So what we do, we take dynamic data and static data, we build fuzzy pattern recognition. I cannot explain it here. It's explaining my book on this topic. And when I do a course that I explain in detail, then we do dynamic conductivity mapping, which is the most important thing. Then we do a spatial temporal interpolation. And from this process, we build geoanalytics model. Let me give you an example of how we do that. So in that particular field in Asia, these are the actual existing production wells. These are existing injection wells that I showed you. So first we go with the injection wells. This injection well, as it produces, which is an actual field, it develops dynamic conductivity map. We're going to do that. So this injection well is impacting these producers as a function of time, right? This injection well is impacting these producers as a function of time. This one, this one, this one. So this is literally all of the injection wells are impacting all of the producers. That's number one. How about producers? Every producer actually impacts in its offset producers as well. This one impacts these, this one impacts these, and I keep going through every single well, and you can see every well that produces anything impacts all the wells around it. This is what spatial temporal is. This is what we do literally in numerical reservoir simulation anyways. Okay, so these are all the communication between all the producers. I showed you the communication between injectors and producers. This is what the whole thing is. This is what we call development of dynamic conductivity. When we identify which one of these communications is better than the other one, then we create what we call dynamic mapping. How do we do that? For every focal well, it has multiple layers, for example. And this is what has been completion in each layer. Then you have an offset well from here. These are the layers, and these are the completion that they're sharing, right? For this one, this is for another well that is offset to this one. And again, this one, let's say in layer one, they do not have completion at all. So this is the share, this is the share, this is the share. When we do that, this dynamic conductivity map becomes this. You see how different, and this has nothing to do with spatial interpolation. This is purely of time interpolation. Now, this is what we developed, the dynamic mapping, right? So here, if this is the gamma ray distribution that I showed you, we did traditionally with the spatial interpolation, this is exactly the same data from exactly every single well log. But then we use this dynamic conductivity plus spatial interpolation. So instead of doing only spatial interpolation, we're doing spatial temporal interpolation. You see the difference. For porosity, this is the difference. For permeability, this is the difference. For initial water saturation, you see the difference. And then when we do that, we can tell you when you drill the wells, what is initial well and where the remaining reserve dynamically maps. So what you saw here, I'm going to show you again from the very beginning. When you come to this beginning, this is initial oil production, right? Original oil production, original oil that exists in that field. And we can, based on what I just showed you, we can say where is more, where is less. This shows you the amount, the volume that it's here. And this shows you the recovery, and this is original oil IP. And then for every month that you produce with these wells that comes in, look, I'm gonna start. You see, the wells are generated, and then they start producing, and that's how it changes. So it tells you at the end the distribution of oil production. Original remaining reserve is here, but that's not enough. You have to do the same thing for pressure. This has done for pressure, injection, and producers. And as you can see, here we go. So based on that, I'm going to stop this because the time is gone. We do history matching, and let me go ahead and show you the result. If you want, I can show you more detail, but the time doesn't allow. So I showed you up to here, the history matching. Let me not go to the detail, but let me tell you what happened. Here's an example. I'm going to stop in a minute. Just let me show you this example. What I'm going to show you is, God knows, you can actually, probably if you attended ATCE, and Annual Technical Conference of SPE in 2020, which was virtual, you probably have seen this. This was provided by the manager of a company in the Middle East that we performed this for. Okay, and I was very happy for him to say, I didn't even know the results that we provided to them, and they did some example. And so what they did, they provided, it's only two slides I'm showing you, I'm gonna stop, but this is exactly what they did and show it. And then we asked them, are we allowed to show this since you already did? They said yes. So here it is. This is the field that they had, and this is the part they were talking about. In here, they had these four, they're comparing these four wells. These are the four wells. These three wells, this one, and this one, was generated by numerical reservoir simulation, where to drill the wells. This one is what TDM, we did, artificial intelligence, where to drill the well. And what's interesting, 2013, 2014, 2015, they drilled these wells during those time. This is when we did it for them, June of 2018. And what he did, he shows this, the production of these three. Watch. First, we're comparing the infill well location recommendation by TDM, AI, and by numerical reservoir simulation, the company did for them, that you all know the company, the most important and common service company in the world. You know who their name is. We're comparing that. So average production, look at the first 6 month production. This is average first 6 month production of these four wells. They did that in April 2020, okay? Here, this is numerical reservoir simulation that they drilled here. This was in February 2013. So until this, it was producing 86 months. This was the first 6 months of this well. This well, in the first 6 months, produced this much oil production on a daily basis. The next one was this well. This well was produced or drilled in November of 2014. So until that day, was 65 months. The first 6 months that this well produced was this much. This is the third one that was produced in or drilled in 2015 for 62 months till that date. So in the first 6 months, this is what this well produced. This is the TDM. This is the one that we recommended to them in June 18. So there was 22 months only until they did the calculation. This is how much this well made in the first 6 months. Again, this is not my presentation. This is the presentation of the that company's manager that was presenting it in. So this was the first 6 months. The same thing, I'm going to show it average of the, because the TDM was producing, the TDM model was producing for 22 months. So we compared all the 22 months, the first 22 months of each wells. You see the comparison. I'm going to stop here. Thank you very much for listening. I don't want to get your time, but there's a lot more that we can go in, a lot of detail on that. If there's any question, I want to provide any opportunity to any question to answer in your question. Thank you very much for your attention.
Thank you, Professor. I think that was very, very interesting session. Thank you all. Deal of information that we benefited from your presentation. And I think that we are having many, many questions into the Zoom chat. Just the principal questions that is about what kind of software that we can use to create such kind of of simulation and modeling?
Sure. The software that we have developed to do this and do all of that using that software is called Imagine. And it's available right now for every company who wants it. And we can show tutorial, all the detail. We actually do it for every company that allows us to do a project for them because it requires a lot of detail, and we need to go to the company and train all of the reservoir engineers. Again, if you're not a reservoir engineer, forget it. There's no way you can do that. But if you are a reservoir engineer, then you have the expertise to do that. Then you have to be exposed to AI and use that software to do exactly what I showed you.
Okay, thank you. We have another questions. We just we have a question for the blind validation. Do you use transfer learning from the other wells?
Okay, so that's the thing. We do not use them for other wells. I can explain it in very detail why. Let me tell you what we do. Let's assume right now we get a project from a company, right? Today is August, right? August of 2022. And let's assume that the field that they give us to do the history matching and optimization and identify where to drill, let's assume that field was started in 2000, right? So from 2000 to now, to 20, means 22 years it's been producing, correct? So what is blind validation? The first thing what we do, we say, okay, let's assume we are not in 2022, we are in 2020. So we take 2 years of the data that's already given to us, the last 2 years, 2020, 2021, and 2022. We take that data and we put it away. We say, okay, that data is not given to us. Let's assume we don't have that data. Let's assume we are in 2020. We go from 2000 to 2020. We build an history match. We do everything that we show, and then we say, okay, what is the blind validation? Because when we get this model, we give it to the company. And when we give it to the company, they're going to do what? They're going to forecast from 2022 to 3, 4, and 5, 3 to 25, that extra. So we have to do the same thing from 2020 to 2021 and 2022. If it works, then we can trust it and give it to the company. If it doesn't work, we know we have something that is not correct yet. So that's what we do. We do our history matching, then we forecast those 2 years of the data that we did not use. We didn't put it in the model. We didn't put it in the software. We didn't do it to help us. That's what blind validation is. We don't do blind validation on a completely new well. Why? Because if we do that, an existing well is an offset well to the other wells that existed. I cannot take that out. I have to put it there to show it how it impacted other wells around it. The new well has not impacted as an offset. Every existing well is going to do it in the future. That's why we don't do the blind validation on the single well, but we do it on all the wells, but at the different time step. I hope that answers your question.
Okay, thank you, Dr. We have another question. Just if you could give us a brief information about proxy modeling.
Oh, that proxy modeling is a completely different story. That I have actually a book just written. It's going to be published in October. What proxy modeling is, as you guys know, that when we do numerical reservoir simulation, it takes a very long time for it to be to make a single run, right? And if you need HPC, why? Because you, as the computers came, and it allows us to do this, the better the computer became, the number of cells became larger and larger and larger. So when we build a model that has 5, 6, 10 million cells for the reservoir that we're modeling, then a single run, even on an HPC, will take 20 hours to run. But if you want optimization, if you want uncertainty quantification, if you want a lot of analysis, you need to run the numerical simulation thousands of times. And if it takes a day to make one run, then it takes 1,000 days. So that's why the problem with management and reservoir simulation, there is a problem with that. And that's why they do proxy model. The original proxy model is what they do. They change the mathematics, make it simple, or they, as BP used to do, they change the number of cells. They reduce the number of cells in order to do it faster. Smart proxy model, what it does, it gives you over 98% accuracy for every single cell, even if you have 10 million cells, right? For every cell in pressure and saturation. So it it repeats your actual numerical reservoir simulator, but it does it so fast. And you can run that 10 million on your laptop for 10, 15 minutes, and you can do thousands of that. That's a whole different way of doing it, AI, but it can help numerical reservoir simulation.
Okay, thank you. Just a last question. Someone is asking, he is a PhD student, and he wants to have that topic as his topic for HCCs. So this software want to be available for him. So he is asking, if he can use the other means like the Python or R language and all other programming or coding to do such process for reservoir modeling and so on. And also he is asking about some recommendations for some textbooks to be used to increase his information about the topic.
Actually, so first and foremost, I used to provide Imagine a few years ago, but there was issues that we had to stop it. So the company does no longer provide Imagine to any university. The only university we provide it to actually is WVU. So my students can't use it. So you're most welcome to WVU and do your PhD here, then you have access to it. It is possible that later on we provide this software to universities as well, but we have to take care of some issues that's outside of this conversation. And so in that context, that's one of the major problems, that it's very hard to use any software to do this, because keep one thing in mind, this requires actual data. And that's one of the reasons, to be honest, that we created a consulting company in 1996, an intelligence solution. The objective was not to make money, I swear. The objective was to work for actual companies and get the data from them to enhance our AI process, because we cannot get actual data. No operating company provides you the data that you can do research with and then publish that. It never happens. That has the problem. That's how, to be honest, that's how we came up with smart proxy modeling, because the data could be generated from numerical reservoir simulation rather than actual data. So that's one of the major problems that we have. Right now, we are dealing with a company to get some actual data for one of my students for his dissertation in PhD. It took 2 years, and there's an issue with getting actual data. That's one of the major problems. So I really don't know what to say. If you do work for a company and you have access to the actual data, first of all, as a consultant, you have to sign that you cannot share it with anybody, which is a fact. But as a person who works for that company, then you can do all of these things. But unfortunately, as a university, it's very hard to do this in academia with actual data. But we will deal with it in a different fashion in our university. I know others cannot. Sorry.
Okay, thank you, Professor. It was very, very interesting session. We all have a big deal of information about that topic, and I hope you more success into your next days, inshallah. Thank you again for your time and effort, inshallah.
Thank you. Just one last item. I would like to, if you Google my name, then you find my email address, which is my first name dot last name, shahab.mohakek@mail.wvu.edu. You can find it on Google. If you have any other question that I wasn't able to answer, if anything I can do to help you, please feel free to send me an email. I'll be more than happy to communicate with you.
Thank you again. Thank you again. Very big for you. Thank you.
Thank you very much. Have a great day. Bye-bye.
Thank you. And also thank you for our attendance. Just a last note, if you want to have a certificate for our webinar today, just you can fill into the form that will be sent into the Zoom chat now. Okay. Just a last reminder, if you wanted to register for our upcoming courses, the link is also will be sent into the Zoom chat now. Thanks again and have a good day.